Hello and welcome to CodeRash with Gaurav. In this video, we are going to look at the basics of data structures. We will look at what are data structures and why do we need them. We will also look at what are different types of data structures, and we are going to implement stack, queue and linked list in JavaScript. So stay tuned till the end and let's begin. To begin with, let us first see what are data structures. Whenever we write code for doing something in JavaScript or any programming language, we often deal with data to do that something. For a variety of problems, you may find the inbuilt data structures like objects, lists, arrays, and maps to be good enough to write code. But for some problems, you will need to store that data in a way that it can be accessed quickly and stored efficiently. Data structures provides you that way. So data structures is a storage that is used to store and organize data. It's a way of arranging data in the memory so that it can be accessed and updated efficiently. Let us look at types of data structures. At a high level, data structures are divided into two types. One is primitive data structure and the others are non-primitive and custom data structures. Primitive data structures are those which usually hold a single or elementary value like a number, string or a character. You can compare these with the elementary or the native data types available in JavaScript. Non-primitive data structures are those which may hold more than one value and which are built on top of primitive data types or the primitive data structures. Now from non-primitive data structures, some can be out of the box available in the programming language, like in JavaScript we have maps, sets, arrays and objects, and some can be purely custom data structures like stacks, queues, graphs and trees. The non-primitive or custom data structures are further divided into two types of data structures like linear data structure and a non-linear data structure. The linear data structures are the structures where the elements are arranged in a sequence one after the other. While in non-linear data structures, there is no sequence as such. Instead, the elements could be arranged in a way that one node is connected to more than one node. Now that we have a basic idea of what are data structures and their types, in this video, let us write some custom linear data structures in JavaScript. Let us begin with stack. Stack is a data structure that follows last in first out principle or LIFO principle. The element that is added at the last is accessed at first. This is like stacking your books on top of each other. The book that you added at last comes out first. Imagine an empty stack where you are pushing elements on top of each other. You pushed 1 and then you push 2 and then you push 3. Now because the element that you pushed at the last remains on top of the stack, when you pull out something from the stack, the element that you added at the last comes out first. There can be some basic operations you can perform on a stack like push, you want to add an element on top of the stack. Pop, for removing an element from the top of the stack. You can check if the stack is empty or not. You can check if the stack is full or not. And you can also peek into the stack. Maybe you want to know what is the top element without even removing it. Let us also look at what are the applications of stack data structure. Why should we even use stack? So though stack sounds like a simple data structure to implement, but it is very powerful and it is very heavily used by our operating systems. Compilers use stacks to evaluate the values of expressions. Any expressions are evaluated using stacks by converting those expressions into prefix or postfix format. JavaScript engine runs our code or the JavaScript code using a call stack or execution stack by reading or interpreting our codes line by line. History in browsers is maintained using stacks. We keep pushing new links visited into the history stack, and when the back is pressed, we pop an item from that same stack. And in the same way, the JavaScript execution happens. Like whenever you are running a JavaScript program, your main execution thread or the global execution context comes into the stack first, and then whatever context that we are creating from our main program, those are then pushed into the call stack. And then from those, if you are pulling out more context, those are also pushed into the stack. And then execution of those execution contexts happens one by one, and those are popped out of the stack and executed till we reach the end of the global execution context. Now that we have a basic idea of what is stack and what are the operations you need to perform on a stack, let us jump into the code and implement these. So we are going to implement stack as a class using constructor function in JavaScript, and which is going to accept max size or the maximum allowed size of the stack as a constructor argument. And we are also going to implement some utility methods on this class, which is empty, is full, push, pop, peek, and also another utility for better debugging purposes while we are writing the code, list elements, so that we at any point of time know what all is present in our stack. So let's begin. And like I told you before, any custom or a complex data structure is built on top of the data structures available natively in a programming language. So we are going to use array, which is available by default in JavaScript, and we're going to make use of that array to create our stack. So let us have an array created here, which is blank for to begin with. And let us first implement a utility which is called isEmpty to check if our stack is empty or not. So we're going to implement isEmpty, and which is just going to return us if the array size is 0. Array dot length, if it is 0, we're going to get isEmpty is true. Now let us also implement if this array is full. So this guy is also not going to accept any parameter, and it is going to return us if the array is full. So we are already getting a max length as an input parameter, so we're going to just check against that max size. If the array has already reached the max size, we're going to return a true from here. Yeah, so that completes our two utilities, which is empty and is full. Now let us write something to push an entry into this stack. So this dot push, this guy is going to take an item which we want to push into the stack, and to do this we will have to first check if there is some space available in the stack or not. If it is not available, we cannot push. So we'll have to first check if there is some space available. So we're going to check if is full, and if this guy returns us true, we're going to console an error saying a standard message which is called as stack overflow. That means there is no space and we cannot push the item which we want to push. And in the else case, that means there is some space available in the stack. We're going to use the native push method of this array, and we're going to push our item into the stack. So we're going to say array dot push the item that we received as an argument. Yeah, so this completes our push utility. Let us write pop, and pop is not going to accept any parameter. It is going to return the item which is there on top of the array. So here also there is a condition. If there is nothing in the array, the pop should throw an error that there is nothing, you cannot pop. So let us see if our stack is empty, and if this guy returns us true, we are going to just console an error which says the stack is empty. And if that is not the case, and if say that there is something in the array, we are going to return the top element, and which we can do using the native pop element, the pop method on this array. So if we do array.pop, this guy is going to give us the last element in that array, and this is also going to modify this original array by removing that from this array. So we return that last element from this array, modifying the original one from here. So this completes our pop. Let us implement a method which says peek. We just want to know what is there on top of this array. So this guy, again the same logic. If there is nothing in this array or this stack, this guy should tell us that the stack is empty, there is nothing to peek. And if that is not the case, we should be able to take out the last element from this array and return it from here. Return array the last element, array's length -1. So this guy should give us the last element without modifying the original array. So you see there is a very similar implementation of pop and peek, just that from pop we are returning the popped element and we are also modifying the original array, but from the peek we are not modifying the original array or the stack. We are just trying to read what is the element on the top and we are returning that. And at this point of time, let us also implement some utility so that we at any point of time can see what is there in the entire stack. So we are going to write a method which is called as list elements, and this guy is just going to console dot debug the array for us. So we should see that entire stack listed in the console. Now this completes our implementation of the stack as a class. We implemented is empty, is full, push an item into the stack, pop an item from the stack, peek into the stack, like let us see what is there on top of the stack, and list elements. Now to use this, let us first create an object out of this class, out of this constructor function. So let me say my stack equals to new of this stack as a class that I implemented, and let me say that I want to keep max size of the stack as 5. Now let us first see if at this point of time what is there in our stack. Let me say list elements, my stack dot list elements, which should return us nothing. It should not log anything. It logged an empty array. So basically our stack is empty. No need of calling console.debug, which we are already doing inside list elements. So now at this point of time, let us see if our utility methods of is full and is empty, they work fine. So at this point, because there is nothing in my stack, is empty should give me true. And if I say console.debug of my stack dot is full, this guy should also give me a false because the stack is also not full. Let us run this. So empty gave me true because there is nothing in the array, and full gave me false because the stack has not reached its maximum limit. Now let us push something into the stack, or at this point of time let us check our pop functionality. So console.debug, we are going to say my stack dot pop. There is nothing in the array and we are trying to pop an element out of it. Let us see what do we get. We are getting the stack is empty, the error which is the stack is empty, which is fair enough. That is what is expected. So at this point of time, let me push something into the stack. Let me push 1 and let me push another element which is 2. Now at this point of time I have 2 items in the stack, and let us see if these guys work as expected. So right now I have 2 elements in the stack. My stack is empty. If it is not empty, I should be getting a false here, and if is full should also give me a false. So I got false for both. Now let us see how long we can keep pushing elements into the stack. So we are going to push some elements here. We already pushed 1 and 2. We are going to push 3, 4, 5, and let's say we want to push another element which is called as 6. Now notice that 1, 2, 3, 4 and 5, till this point I have reached the maximum limit I can push into the stack. So as soon as I try to push 6 into this, I get a error saying stack overflow. Now let us see at this point of time how does my stack look like, how does the entire list look like. So if I list all the elements, I get 1, 2, 3, 4, 5. Fair enough. Now let us get an item out of the stack. Let us say my stack.pop, and we will have to console debug this to see what did we pop? So if we run this code, my stack.pop, so we did something wrong in the pop. Okay, we should be using array. Now if you run this code, we got 5. When we said my stack.pop, we got 5 because 5 was at the top of the array or the top of the stack. Now at this point, if we want to see what is there on the top of the stack, we should be able to do console.log my stack.peek. This guy should tell me what is there on top of the stack, and after popping 5, I should be having 4 on top of the stack. So let us run this code. We should be using debug because I have disabled logs from here. Yeah, so we got 4. So you see that we are able to implement stack as a class, having its member functions as is empty, is full. We are able to pop an element out of the stack. We are able to push an item into the stack, and we are able to see what is there on top of the stack. And just for better debugging purposes, we are trying to list out all the elements. So this completes our stack implementation. The next data structure we are going to look at is a queue. Queue follows first in first out principle or FIFO rule. The item that goes in first comes out first. Imagine queue being like a ticketing queue outside a cinema hall, where the first person entering the queue is the first person who gets the ticket. So any item that gets added to the queue always gets added from the back, and this process is called as enqueuing. Any item that goes out of the queue is always goes out from the front of the queue, and this process is called as dequeuing. There are some basic operations you can perform on the queue, like we saw enqueue and dequeue. Likewise, you can see if the queue is empty or not. You can see if the queue is full, and you can also peek into the queue to know what is the value at the front of the queue without removing it. You just want to know what is at the front of the queue. Let us look at some applications of the queue data structure. The queue is very heavily used by the operating systems for handling the context switching. Any kind of CPU scheduling or disk scheduling, any kind of interrupt handling, or data transfer asynchronously between two processes. All this is done by our operating system using queues for different purposes. So the things that are to be performed in parallel, they are put into the queue and they are executed one by one. Likewise, you would have seen that whenever you call a call center of a company, you often hear a message that you are in a queue, please wait. So this is how any process or a task waiting for execution is put into a queue, and then whoever is executing it picks up the items from the queue one by one, or the tasks from the queue one by one, and executes them. So now that we know what is a queue, what all basic operations you can perform on a queue, let us jump into the code and implement a queue and its operations. Like we implemented stack, we are going to implement queue as a constructor function which defines a queue class for us, and we are going to accept a max size for our queue, and we are going to implement some utility methods which are is empty, is full, enqueue, dequeue, peek, and a method for listing down the elements. So let's begin. And again, we are going to use a native array to support our queue. Let us initialize that with the blank array, and we are going to implement utilities, which is empty. This is going to just say if the array is empty or not. If the length is 0, we are going to return true, and we are also going to check if the queue is full, and we are going to check that against the max size that we are getting. So array dot length, if it has reached the max size that we are getting, we're going to say the queue is full. And now let's implement enqueue so that we can add an item into the queue. So this guy is going to accept an item to be added to the queue, and we're going to first check if the queue is full. So we're going to call this dot is full, and if this guy returns us true, that means there is no more space available in the queue. We are going to just console dot error, and we are going to say the queue is full. And if that is not the case, and if we have space in the queue, we are going to say array dot push the item that we are getting. So we add it to the list. Now let us implement a dequeue, which is not going to accept any parameter, and it is going to return us the item at the front of the queue. Now here also again we are going to check if the queue is empty, that means there is nothing to dequeue. We are going to throw an error. So we are going to check if it is empty. We are going to say the queue is empty, and if that is not the case, we can dequeue something from the queue. We are going to return the first item that we added in the queue, which is going to be the 0th index always. So we can use a utility available on the array, which is shift. So this guy is always going to give us the first item that we added in this array, and this guy is also going to modify our array that we are using here. So similar to dequeue, we are going to implement peek, which just tells us what is there on the top of the queue. So again, peek should work only if there is something in the queue. Otherwise, we are going to return the first element in the array. We return the first element from here. So like we saw in the stack, again here also dequeue and peek, they are very similar operations. In dequeue, we are modifying the original array and popping an item from the array from the beginning. Array.shift gives you the first item of the array and shifts the array towards the left hand side. So this guy is going to modify the original array, and this guy is just going to tell you what was the first item that you inserted in the queue. Similarly, let us implement list elements, which is just going to log all the elements available in the queue. And that's it. With this we have completed the implementation of queue as a class, where we have utilities like isEmpty, isFull. We are able to enqueue an item into the queue. We are able to dequeue an item from the queue, and we can also peek into the queue to see what is at the front of the queue. Now to use this, I'll have to instantiate this class. Let me call a new on the queue, saying my max size of the queue is 5, and let me enqueue 2 here. So right now I have added 2 as an item into the queue, and let me add another item into the queue, which is 3. Now if we try to see what is there at the front of the queue, we should be using my queue dot peek. Tell me what is there in the front of the queue. This guy should give me 2, because that is what I inserted first. So if I imagine this queue as a ticketing queue, the person 2 got added first and 3 later on. So if I am at the front of the queue and I want to know what am I looking at, I should be looking at 2. So this guy gave us 2, and let us also list this guy as an array or we can just call list elements my queue dot list elements. This guy should tell us what is there in the entire queue. We should be using debug. Let us see. Yeah, so we have 2 and 3 in the queue, and 2 being at the front of the queue because we are looking at the front of the queue. Now let us see how many elements we can keep enqueuing. So we added 2, 3. Let us add 4, 5, 6 and 7. Now till I add 6, I'm good. As soon as I try to add 7, I get an error which says the queue is full. Now at this point, let us see what does our queue look like. Our queue contains 2, 4, 5, 6 and 7 got rejected because the queue was full. And if we try to see what is there at the top of the queue, what is the guy who is going to move out the queue first, it should still be 2 because I inserted this item as the at the very beginning of this queue. So this guy again gives me 2, which is what we expect. So with this you saw that we are able to generate a queue class which has these utility methods. We are able to enqueue and dequeue items. We are able to also enqueue and dequeue conditionally, provided that the queue is either empty or is full. Like if you have the space, you should be able to enqueue. If not, you should be able to throw an error. Same is the case with dequeue. If you have something, then you can dequeue, otherwise not. Peek allows us to look at the front of the queue. So that completes our queue implementation. The data structure we are going to look at next is a linked list. A linked list is a linear data structure that includes a series of connected nodes, where each of the nodes stores the data and the address of the next node. So imagining a list being starting at head, where the head pointer points to the first node of the list, and then each of the item points to the address of the next node. So that you can imagine it like a chain, where if you start from the head, you are able to traverse that entire list using the pointers. I get the address of the next node from here, I reach there, and then I get the address of the next node, I reach there, and when I reach the last element of the list, the next pointer points to null. That determines the end of the list. So head and the last pointer are very prominent here, where the head points to the first address of the node and the last node is identified by the fact that it points to a null pointer. So this is how uniquely you can identify the first and the last element of the linked list. Usually when you are dealing with linked list, if you get the address of the head pointer, that is enough, because you can start traversing that entire linked list using the head pointer till you reach the null. There are some basic operations you can perform on a linked list, like insert. You can add a node at any given index or at the tail. You should be able to delete an item from the linked list at a given index, or you should be able to delete an item from the last. You should be able to traverse the entire linked list and list all the items and see what is there in each node. You should be able to search and find where does my given value lies at the linked list. We should be also able to determine the length of a linked list. Now this becomes a special operation on linked list because linked list is not maintained using arrays, and because this is a contiguous memory allocation where each node points to a different one, we need a special operation to determine the length of the linked list that we are going to see while we code. Let us look at some applications of the linked list data structure. Any kind of a dynamic memory management that is done using linked list. If you remember using calloc function in C, that uses a lot of linked list to maintain a kind of a list of storing the addresses of the partitions of the data. So polynomial manipulations are represented using linked list data structure. The allocation of files, a large file in the memory may not be stored at one place. It can be stored fragmented way at multiple places on the either in the hard disk or in the RAM. So we need a linked list to provide a mechanism to link all the scattered parts together in a sequence. Like the first part of the file lies here and then the second part lies here, and these addresses can be very differently located on the storage locations. So linked list provides you a way to link all these things together. So linked list is very heavily used in memory management, dynamic memory management, or fragmented memory management. Now, given the fact that now we know what is a linked list, what are the basic operations you can perform on the linked list, let us jump into the code and implement these. To create a linked list, we will be using a function which is called as node. So this becomes a constructor class, constructor function for us, which is going to provide us an entity which is called as node. This is going to have two values, two members inside that, which is a value and the next. Like we saw in the linked list definition, each and every item in the list is defined by an entity which is called as node. It contains its own value and pointer to the next node of its own type. So we are going to make use of this helper class which is called as node. And our linked list we are going to define as a class using a constructor function which is going to have some utilities like insert at, traverse, length, delete at any index, and search within that linked list. So let us begin writing our linked list. Let us start with a entity which is called as head. Let us initialize this to null. So this signifies that right now our linked list is empty because there is nothing in the head. Let us begin inserting some node into this. So let us have a method which is called as insert node, and this guy is going to take a value as an input which we want to insert in the linked list, and this guy should first check that if I am inserting the first value, that means head does not exist. So if there is no head so far, so what I'll do is I will create a head now. So head equals to this dot head equals to a new node, and I pass on the value which I got. So this guy created a blank node and we assigned it to the head of the linked list. Now whenever you initialize a node, whenever you create a new node, the next is always null. So remember that. So whenever we are creating a new node, the next is always null. We're assigning a value, and based on where we want to put that node, we will be adjusting the next pointers. And if that is not the case, if the head exists when we are getting insert node, if the head exists, that means there are elements in the list, and now we may want to traverse till the end of the list to insert this node. And how do we traverse? Is through the node pointers. So we are going to maintain something called as current pointer, initialize that with head, and then we are going to traverse till the end of the list. So we're going to say while current pointer dot next does not equals to null, we will be keep on going till the end of the list. So we keep incrementing the current pointer to the current pointer dot next, and when we exit this while loop, we are at the tail of the list. So when we are at the tail, we should be creating a new node and assigning it to the tails next. So current pointer dot next equals to new node of this value, So say that, let us break it down. So say that your list looked like this, and now you are inserting a node, say 4. Now post this, our list should look like this, 1, 2, 3 and 4. Now doing this while loop, what we are saying is we want to traverse till the end of the list, till the next pointer, till the current pointer's next is not null. So till we reach 4. So in this case we are going to traverse this entire list till we reach the node 3, and when we exit this while loop we will be at the node 3. We are creating a new node and we are just assigning 3 is next to 4, and because we instantiated a new node, fourth node's next already points to null. So we just created a new node and established a link between 3 and 4 saying 3.next equals to 4. This is how we were able to insert a node. Now this completes our insertion of the node. Let us quickly write a method which is going to traverse through the list. And this guy does not take any input. This guy just traverses throughout the list, and let us do the same thing. Let us maintain a current pointer. Let us initialize that with head, and we will go through each node. So while current pointer does not equal to null, that means we have not reached the end of the list. We will keep going further, and we will just say current pointer equals to current pointer dot next. We will keep moving forward in the list, and at the same time let us log what we got. Console.debug, we will log current pointer dot value. So at every node we are starting with head, and at every node we are logging the value and then moving forward. Let us test this out. Now at this point we have a linked list created. We are able to insert nodes into the linked list and we are able to traverse that. Let us try this out. For doing that, I'll have to create an object of linked list. I'll have to instantiate a linked list. So let's do that. List equals to new of linked list. Right now my linked list is empty. Head should be pointing to null. Let me insert a few nodes quickly in this. I am going to do that through an array. I take each element and I'll just say list dot insert node that element, and let us traverse this. So list dot traverse should tell us what is there in the list currently. Let us try this out. Okay, so we inserted 1, 2, 3 and 4 into the list, and traverse told us that these are the items in the list. To make it more clear, let us also log what are the next node values, the next pointer values. So let us say current pointer dot next. Let us see what lies in the next pointers. So we start at the head, which is the root node, which is 1, and then that is the value, and we are logging next. So next is a node and whose value is 2, and that is further pointing to a node. If we look at the node 2, the value is 2, and the next pointer is a node whose value is 3, and it is further pointing to another node. If we look at node 3, it is a node of value 3, and the next value is a node which is having a value of 4. And if you look at 4, this guy points to null. That means we have reached till the end of the list. Right now we have 4 elements in the list, and we are able to insert nodes into the list, and we are able to traverse them. Now quickly add some basic utilities to this. We are going to add this dot insert at head. Let us try to add a node at the head. So we got a value. This is going to be simple, that we are just trying to add a new head to the value, to the linked list. Now let's say at this point of time you do not have any head. If there is no head, then this is the first node you are trying to insert, and you are saying insert that at the head. So we are going to say this dot head equals to a new node with that value, like we did before. and that if that is not the case, that means there are elements in the list and you already have a head set. You are trying to insert a new head, a new value at the head. So what we are going to do is we are going to create a new node, passing the value which we got, and we should be doing new node dot next equals to head, and we also want to keep the head, this variable, maintained in our list. So we are going to say head equals to new node. Let us break it down. What we did here was, let's say you were at such a list while you were trying to insert at head. Now let's say I want to insert a value 4 at the head. Now post this, my linked list should look like 4, 1, 2 and 3. So this is how my linked list should look like. So what I'm doing over here is I'm creating a new node. Whenever I create a new node, the next is always pointing to null. So my new node's next I am saying head. So now 4 starts pointing to 1, and the head, the variable that I'm maintaining at the class level, that I reset to 4 now. So at any point of time, if I ask the linked list what is your head, it will start saying 4. So this is how it works. So let us try this out. We had a traverse. Let us say list dot insert at head. We want to insert 4, and then let us see list dot traverse. Inserted head, this dot head, okay, this dot head and this dot head. So we had 1 2 3 4 in the list, and now we have 4 1 2 3. So we were able to insert at the head. Now using the same concept, we are going to have a utility which is going to insert at any given index, where it can be either head, it can be tail, or it can be any given index. So let us try to implement that. So this dot insert at, this guy is going to take a couple of inputs. First one is going to be the position and the value which we want to insert. Now take a note here that we are asking for a position, not an index. So position 1 would mean head, that means index 0. So don't confuse between index and head, index and position. We are asking for a position. What position do you want to insert at? And position would start with 1. Now we have already solved this problem for position equals to 1, which is the head. We already know how to insert at head. So if position is going to be 1, we are just going to say insert at head. Insert at head the current value which I am providing. Otherwise, what I'm going to do is I'm going to have a same concept again. I'm going to iterate through the list using a current pointer starting with head, and now I'm going to traverse, and I have to traverse till position -1. We will look at why. So let us maintain a traversal counter, and because we have already crossed head, we are not considering the head pointer here. Let us initialize traversal counter with 1. That means one node is already traversed. Now we're going to say while traversal counter is less than position -1. The -1 is of significance here because we do not want to go till the position. We do not want to, let's say we want to insert a node at position 3. We do not want to go till position 3. Otherwise, we'll lose the context of pointers. We are going to go till the position -1. Let's say we want to insert a node at index or a position of 3. We are going to go till the position of 2 using this loop. So as soon as we are inside, let us increment our traversal counter. keep progressing further, like current pointer equals to current pointer dot next. We'll keep going further, and there can be a case where I am given a position in this method which is out of bounds. Let's say there are only 4 elements in the list and I want to insert at position 6, which I cannot. So I'll have to throw an error from here. So current pointer, as soon as it becomes null, we should be throwing an error, console.error, the position provided is out of bounds. Now when we exit this while loop, we are at position -1. So now what we will have to do is, let us maintain in a temporary variable the next pointer of the current pointer dot next, and we are going to say current pointer dot next equals to a new node that we will create with the value provided, and we are going to restore the link, the broken link, saying current pointer dot next equals to next in the link. So let us break it down, what exactly we are doing here. Say that you had a list which looked like this: 1, 2, 3 and 4. Now we want to insert at position 3 an item 6. Post this, our linked list should look like 1, 2, at position 3 item 6. So 6 and 3 and 4. This is how our linked list should look like. At third position we are trying to insert 6. So 1, 2, 3, 1, 2, 6 and 3, 4. Now we are trying to traverse till the position -1. So we are stopping at node 2 here. Once we exit this loop, we would be stopping at node 2. Now what we are doing is, we are keeping in memory what would be the next pointer of my current pointer. So current pointer is at 2. I kept in memory in the temporary variable the pointer to the next pointer of 2, which is 3. And what I did was, I created current pointer dot next, a new node. So 2 starts pointing to a new node which is 6. So 2 starts pointing to 6, and because I have already kept 3 in a temporary variable, I can say that 6 can start pointing to 6. Sorry, 6 can start pointing to 3 now. So basically what we are saying is, we are saying 1 points to 2, 2 points to 6, and then 6 points to 3. And how we are maintaining that is, because our current pointer stopped at 2 and we created a new node here which is 6, 2 points to 6. So when we are at 2, we should be able to say current pointer dot next, which is 6, dot next, which is 3. So we are saying current pointer dot next equals to next in the link. This is how we are completing the broken chain. So let us try this out. List dot insert at, let's say at position 3 we want to insert 6, and let us traverse this. To keep it cleaner in the console, let us say console.debug. After insert at. Okay, so we had 4, 1, 2, 3 in the list. Now what we are doing over here is, 4, 1, 2, 3 and 4 in the list, because we had 1, 2, 3, 4 in the list, and then we added 4 at the head. Now the list is like something like 4, 1, 2, 3 and 4. And now we are saying at position 3 I want to insert 6. So at this point my list looks like 4, 1, 2, 3, 4. This is how my list looks like. and I'm trying to insert 3. I'm trying to insert 6 at position 3. So it should look like 4, 1, 6, 2, 3 and 4. So let us look at what we got. 4, 1, 6, 2, 3, 4. So it correctly inserts at the provided position. Now let us try out some edge cases. Like, are we able to insert at the head? Let us try to insert at position 1. Let's see what we got. We got 6, 4, 1, 2, 3, 4, which is what we expect. So 6 got inserted at the head. Now let us see if we are able to insert at index which is out of bounds. Let's say 10. I get an error which says position provided is out of bounds. We should be returning from here. Okay, so we get an error console which says the position provided is out of bounds. Now what we are doing over here is we are trying to go till the position -1, and if the position itself is out of bounds in that list, we will end up with current pointer being null, and whenever that happens, we are breaking the loop and we are just logging the error, so we do not fall into those null case. So let us see if we are also able to insert at the tail. Now at this point of time, our tail should be at the position 1, 2, 3, 4, 5. So let us try to insert at position 6, which should be the tail. Let us try to run this code. So we have 4, 1, 2, 3, 4, and post this 6 should be inserted. 4, 1, 2, 3, 4 and 6 got inserted at position 6. Now if I increment just 1 further, this should become out of bounds. Yeah, so I'm not able to insert at 7th position because right now my list is only having 5 elements and the position would be ending at 5. So I can insert at the tail saying insert at position 6, but beyond that I cannot insert. Now let us add more utilities to our linked list. We're going to implement a method which is going to delete an item at a given position. Like the logic is going to be very similar to how did we insert at a position. We're going to delete a position from the linked list. So let us begin writing that method. This dot delete at position. This guy is going to take a position as an input, and what we are going to say is we're going to treat the head specially. If position is 1, that means we are trying to delete the head. We are trying to delete the node which is at the head currently. So we will have to point to the heads next equals to head dot next. So all we did here was we started pointing the head to its own next. So this maintains the position, the deletion of position at 1. Now if that is not the case, if you are not trying to, if you're trying to delete at a further position ahead of the head, let us see how we can do that. We're going to have the similar logic like we had for insert at. We are going to traverse till position -1. So let us have a current pointer. Let current pointer equals to head. Let us initialize that with head, and let us also have a traversal counter to be initialized with 1 because we have already crossed position 1. Now let us have a while loop and let us iterate till the traversal count is less than position -1. Similar as insert, because we want to stop this loop at position -1. So what we're going to do over here is we are going to keep traversing further. So traversal counter ++, we want to keep incrementing the traversal counter because we want to keep a track of how much we have traversed so far, and we are going to say current pointer equals to current pointer dot next because we want to keep incrementing or keep going further in the list. Now similarly, like in insert at, we can reach an index which is out of out of bound in this case. So current pointer dot next, if that goes out of bounds here, we are going to say console dot error, and we are going to say the position provided is out of bounds. And when we exit this while loop, we are going to be at the position -1. So what we are going to do here is current pointer dot next equals to current pointer dot next dot next. So we are breaking a link at the position. We're going to say we stop at position -1, and then the node which is at the position -1, we start pointing that to the next dot next, so that the link is broken and now this child becomes orphan. So the current pointer dot next, which was earlier the position which was to be deleted, that becomes orphan now, and that is how it is deleted. It is taken away from this chain. Let us try this out. Now let us have a log which says after delete at, and right now our list looks like 4, 1, 2, 3 and 4. So let us try to delete list dot delete at position. Let us see if we are able to delete the head, and let us also traverse this. List dot traverse, let us see what do we get. So we had 4, 1, 2, 3 and 4 in this list, and after deleting at position 1 we got 1, 2, 3 and 4. So that means our head node was deleted. Now let us try to delete the tail. Right now the position of tail would be 1, 2, 3, 4 and 5. So let us try to delete a node at position 5. We got an error, I think, again for this dot head. Yeah, let's correct that and run again. Okay, so we had 4, 1, 2, 3 and 4. Now this guy was the last node, and at the position 5 we are trying to say delete at position 5. Now we have 4, 1, 2 and 3, and 3 starts pointing to null. So 3 becomes our tail node. So we are able to delete at the tail as well. Let us try to see if we can go out of bounds. Let us try to see if we can delete at 6. The position provided is out of bounds. So similarly, we should be returning from here as soon as we get this. So we are not able to delete at position 6. It says index out of bounds. And if we traverse the list again, it is the same, unchanged. 4, 1, 2, 3, 4. 4, 1, 2, 3, 4. So delete at any position works. Let us implement another utility which is for searching any given element in the list. So let us do that. This dot search, it is going to take a value as an input. We want to find out the position of this value or the index of this value. So let's say let current pointer is to be head. Let us start with head, and let us have a flag that says it is found or not. So let us initialize that with false, that it is, let's say, not found. And we are also trying to find out what is the index of it, at what index this particular value is found. So let us have an index initialized to be 0. Now let us go through the linked list. While the current pointer is not null, let us keep progressing further, and let us see if the current pointer dot value, if I have already reached a node whose value is matching the value that is to be searched for, I would say found to be true, and break the loop from here. Otherwise, I am just going to keep continuing the loop, saying current pointer equals to current pointer dot next. Let us keep going further in the list and keep incrementing the index. Now when I come out of this loop, if the value is found, I will have found equals to true and index correctly set to the current pointer. And if it is not found at all in this loop, the found is going to remain as false, because we are only setting it to true if it is found. So let us check that. If the element is found in our list, we are going to return the index where it was found. Otherwise, we are going to return -1. Like usually how how you find anything in an array, how does that behave? Index of kind of an implementation. Either it gives you the first match index or it returns you -1 in case of it is not found. So let us run this and try to search. Let us do a quick spell check and let us try to search this. Okay, we already have a lot of traversals logged out. Let us comment that out to clean up our console. Let us say list dot search. I want to find where is my node 2, and let us console what it gave us. Console dot debug. Item 2 was found at index, whatever we are getting from that. Search 2. Let us see if we get the right result. Item 2 was found at index 2. So 0, 1, 2. Index was 2. And let us see if we are able to fail this by saying, let me find something which does not exist in the list. Let me try to find 11. And let us see if we get -1 as a search result for 11. So item 11 was found at index -1. So this guy is going to return us -1 if it is not found. So let us look at whatever we have implemented so far. We are implementing a linked list. We are able to insert nodes one after the other. We are able to insert at head. We are able to insert at any given position in the list. We are able to delete at any given position. It can be head, it can be tail, or it can be anywhere in between. We are able to search for a value in the given linked list. We are able to find the index, the first match index where it is found. We are able to traverse in that list. Yeah. And like I told you before, there is a special case of determining a linked list length. And let us look at how do we determine a linked list length. So we will have to go through each and every item in the list till we reach the end, and then we'll keep incrementing a counter that we maintain. So let us do that. Current pointer equals to, let us start with head. Let us say our length is 0. Let the length equals to 0, and let us start traversing while the current pointer is not null. Let us keep going ahead. Let us keep incrementing the length, and let us keep going forward in the list. Current pointer dot length, current pointer dot next. When we are out of this loop, we would have already traversed all the nodes, and we just need to return the length from here. So let us try this out. Let us say console dot debug list dot length. Let's see what we get. Where did I write length? Okay, so this dot head, and let us try to run this again. So length is 5, because in our list right now we have 4, 1, 2, 3 and 4. The list length is 5. Now length becomes a special case and a thing to remember in the case of linked list, because if you are dealing with native data structures like array, you can directly access the length. But for determining the length of a linked list, you have to traverse through all the elements. This is why you should be remembering how to calculate the length of a linked list. Now, there can be many ways of doing so. We were writing the linked list as a class from scratch. We could have had a pointer here, or a counter here, which says that what is my current length. We'll start it with 0, and whenever you are inserting, increment that. Whenever you are deleting an item from the list, decrement that. This could be one way of getting to know the length of a linked list. But in many of the cases, in many of the coding exercises or the interview questions that you're going to solve, you are just going to get a head. People are just going to say that this is how my node looks like, and this is the head pointer of the list. You need to solve a problem. Now, for many problems, you might want to find what is the length of the list. Now, there may be not a native method available on the linked list data structure that we have. So you should be knowing how to calculate the length of a list. So this completes our coding exercise for the linked lists. Let us summarize what we saw in this video. We saw what are data structures. We saw why do we need them. We also looked at different types of data structures, linear versus non-linear. We also saw what are primitive versus custom data structures that we write. We saw what is a stack, how it is implemented, and what are its applications. We saw what is a queue, its applications and implementation. We saw in detail what is a linked list, its applications, and we implemented all basic functionalities on linked list. So what next? We'll be looking at some non-linear data structures in the videos upcoming. We'll be looking at tree, we'll be looking at graph, and we'll also look at some algorithms closely. We often compare algorithms on the basis of big O notation, their time complexity, their space complexity. We will also see what are these and what is their relevance. How do we compute time complexity and space complexity of the code that we are writing? We will also look at what are these algorithms and how do we classify them. So stay tuned. Thank you for watching this video. I hope you liked it. And if you did, please do leave a like. Share this video with your friends and subscribe for more such videos. Tell me in the comments what topic should I cover next. Till then, happy coding, and I'll see you in the next one.